So in section 2, we're going to take a look at normal distribution. So a normal distribution is any distribution which is symmetric with the mean and median lying at the top of the peak of the curve. So this is your typical bell curve is your normal distribution. So there's an even distribution of data above and below your mean and median. So, but they don't all look the same. So the mean and the standard deviation determine the shape. So the higher the standard deviation, the more spread out the curve becomes. So if we're looking at an example here, so we have a different color graph. So we look at the one that's the skinniest has a standard deviation of 0.3. So it's a really small standard deviation, which means the curve is a lot skinnier. Compared at our blue one, which is hard to distinguish between the blue and the black, but the blue one has a standard deviation of 1. It's a little bit fatter. So they all have a mean, so in this case, we're looking at graphs that have a mean of 0, just to kind of compare. But depending on what the standard deviation is, that determines the shape of your normal distribution. So whatever the normal distribution is, though, there are still many properties that all of them share. So one of the biggest ones is that the area under all of our normal distributions is the percent of data values in that region. So when we're kind of looking at what this means, so I have my density curve here. So we have our mean, in the middle. And what it does is it splits up the graph in half, and you have, so we have, the area above the curve is 50%. And then we can do an area below the curve, and then we can say, or we can do just a specific amount. So if I specifically want to look at this x value and its area below that. So we can look at values above and below the mean. We can also look at specific values, like how much of the area falls below this specific x value. Which is what we're going to take a look at in this section. So just in general with bell curves, it is bell-shaped. A normal distribution is bell-shaped. The mean, median, and mode are all the same, and they're at the center. It is symmetrical about the mean, and it is continuous. So there's no holes or gaps, and it never touches the x-axis. It may get very, very, very close to touching the x-axis, but it's never going to actually touch. So there are a couple rules. The most common rule is the 68, 95, 99.7 rule. So how it works is that in any normal distribution, 68% of the data is going to lie within one standard deviation of the mean. So if we're looking at this picture, the blue area is the 68% of the data. Then if you go within 2 standard deviations of the mean, 95% of your data is going to lie within that. So that it does include the blue area. So the purple is the additional amount of the area. And then lastly, the 99.7% of the data lies within 3 standard deviations of the mean, which is the green. So for example, so the green does also include the blue and the purple. It's just the additional area that it includes. So if I wanted to look at an example, so let's say we have a mean of 50 and we have a standard deviation of 2. Okay, so 68% of my data lies within 2 standard deviations above and below the mean. So that means 1 standard deviation above, 1 standard deviation below. So that's 48 to 52. And then 95% of the data lies within 2 standard deviations of the mean. So 2 standard deviations would be 4. So that would be 46 to 54. And then lastly, 99.7% of the data lies within 3 standard deviations, which would be 6, which would be 44 to 56. So it's a really cool rule that we can use if we know how many standard deviations we are above or below the mean. We know what percent of my data has to lie within that many standard deviations. Of course, we are not always going to be specifically 1, 2, or 3 standard deviations above or below the mean, which is where we're going to talk about that in a little bit. So let's look at an example. So the weight of babies is approximately normal with a mean of 8.2 pounds and a standard deviation of 1.7 pounds. Between what two weights do 68% of all babies fall? So 68% is 1 standard deviation. So we take the mean, we add and subtract 1 standard deviation, and that will give us our range. So for us, our mean is 8.2, and we're going to add and subtract 1.7. So when we do 8.2 minus 1.7, we get 6.5. And then when we do 8.2 plus 1.7, we get 9.9. So 68% of babies weigh between, 68% of all babies fall within 6.5 and 9.9 pounds. Okay? Between what 2 weights do 99.7% of all babies fall? So that's the mean plus or minus 2 standard deviations. So that's 8.2 plus or minus, and then 1.7 times 2 is 3.4. Sorry, 99.7 is 3 standard deviations. So 3 times 1.7, which is 8.2 plus or minus 5.1. So 8.2 minus 5.1 gives us 3.1, and then 8.2 plus 5.1 gives us 13.3 pounds. Okay. So that's using the rule to find a range of weights, but we can also say what percent of babies weigh more than 11.6 pounds. So this is where kind of a density curve is going to be helpful. So in the middle here we have our mean of 8.2. Okay. 1 standard deviation gives us 9.9. 2 standard deviations is 11.6, and then we can also work our way below. So 1 standard deviation below is 6.5. 2 standard deviations below is 4.7. So we know that within 1 standard deviation, so the 6.5 to the 9.9, that's our 68%. And then we know if we go 1 standard deviation farther, so the 9.9 to 11.6, we know that's our 95%. So what that leaves us with is above the 11.6 and below the 4.7 has to account for the last 5% of our data. So if we're talking about specifically greater than 11.6, so remember, above 11.6 and below 4.7 have to account for the rest of the 5%. So we evenly distribute that, so that means above 11.6 has to be 2.5% of our data, because we have to evenly distribute half of it above 11.6 and half of it below 4.7. So, like I already talked about, 68, 95, 99.7 rule is very good, but it only uses 1, 2, or 3 standard deviations. So not a lot of it lays specifically that many deviations. Some of them are decimals, like we looked at in 2.1. So for example, 1.3 standard deviations. So what we do here is we use a z-score for this, or a standard score. So remember, referring back to the 2.1, your z-score is the number of standard deviations you are from the mean. So the way we use that is, it's called a standard normal distribution. So it's a normal distribution with a mean of 0 and a standard deviation of 1. And all normal distributions can be turned into a standard normal distribution using z-scores. So we're going to use that table for any standard deviation that's not 1, 2, or 3 exactly. So we use the z-score to find the area or the probability under certain parts of our standard normal distribution curve. So in the table that you were given, we're only talking about area to the left of a particular z-score. So to the left means always less than a certain z-score. So we're going to have to pay close attention to whether or not we're talking about above or below a certain z-score, so we know what to do with our percentages. So we want to know what percent of the area is greater than a z-score of 1.6. So we have our mean of 0, and then we have a z-score of 1.6, which is obviously above, and we want to know what area under the curve is above 1.6. So what percent of that area? So if you look at your z-score table, you go to 1.6, and then you have to have 2 decimal places. So for our purposes, it'd be 1.60. And remember, this is always the area under the curve. So it's 0.9452. So the percent that's to the left of 1.6 is 0.9452. So we want to find the percent greater. Remember, area under the curve is always 100%, so we do 1 minus the 0.9452. And we're going to get 0.0548, which as a decimal is 5.48%. So the area above the curve is 0.0548. Because remember, the entire area under the curve has to be 100%. We can also do percent of areas between 2 z-scores. So we have our curve, the middle is 0, 2.13 is above, and then negative 0.2 is below. We want the area between these 2 values. So we want the area in between here. So what we have to do is we find the percent underneath each of these. So the percent that's below 2.13, so we go to 2.1, and then we go over to the decimal of 0.03, and we get 0.9834. Then we go to the back and we look for the area under the curve for negative 0.20, and it's 0.4207. So if we want the area between the 2, we subtract. So we do 0.9834 minus 0.4207, and that's going to give us the area between, which is 0.5627, which is 56.27%. Okay. And then lastly, what percent of the area is greater than a z-score of negative 1.81? So again, we have our curve with our mean of 0 and negative 1.81. So remember, our graph our table itself is going to give us the area below, but we want the area above. So we want the area above So if we look at negative 1.81 from our table, we get 0.0351. And we want the area above, so again, we're going to do 1 minus 0.0351. And we're going to get 0.9649. So 96.49% of our data lies above a z-score of negative 1.81. So this is just interpreting z-scores from the table without a certain situation. It makes a lot more sense when you're actually looking at a situation to talk about what these percentages mean in relation to something specific. So we can also go the other direction. So you're given a percentage and we want to know what the corresponding z-score is. So what you're doing is you're given the area and you want to find your z-score. So want to know what z-score cuts off the bottom 5% of the area under a normal curve. So we draw our curve and we have our mean of 0 and we have some z-score that gives us the area. And what we want to look for is a z-score that's close to 0.0500. So we may not find a specific z-value. What we want to do is find the z-score that's closest. So we look for 0.0500. And we want to get as close as possible to that. So negative 1.65, which is not exactly 0.0500, but it is really close. It's 0.0495, which is really, really close to 0.0500. So then on the next one, we want to know what z-score cuts off the top 20%. We have our curve with our mean of 0, and we have some z-score. So the top 20%, remember z-score tells us the area under the curve, so we want the top 20%, 0.200, which means we're looking for the z-score that gives us 0.8000. Because remember, z-scores are always the area below the curve. So we're going to be looking for a positive z-score this time, because we're above the mean. And we're looking for something that's closest to 0.8000. And that's going to be 0.84. It has a z-score of 0.7995, which again, we may not find an exact z-score, but we want the z-score that's the closest. Lastly, we're looking at the z-scores that cut off the middle 50% of the area under the curve. Okay, so we have our mean of 0, and we have a z-score above, and we have a z-score below, and we're talking about the middle 50 here. So what that tells me is, so remember, in order to find a middle, we subtract the upper and the lower. So it means that I have to take, this is 0.5000. My below is going to be 0.25, because the only way we're going to get the middle 50% is if we're taking the upper 25 and the lower 25, and that gives us the middle. So we're looking for a z-score that's close to 0.2500. And the closest one is going to be negative 0.67. But this time we have to do plus or minus, because remember, when we find a middle 50%, we subtract an upper and a lower. So 0.2500 below also means I'm going to have, for a negative, means I'm also going to have a positive 0.2500 above. So plus or minus 0.67 is going to be my z-scores, because when I use the positive 0.67 and subtract negative 0.67, I'm going to get the middle 50%. So we can take any normal distribution and transform it into a standard normal distribution by using our z-score formula from 2.1 and our table of values. So just to kind of refresh, the formula from 2.1 was z equals x minus the mean over our standard deviation. So if the scores for a test have a mean of 100 and a standard deviation of 15, find the percentage of scores that fall below 112. So it's the same thing as finding the probability. So we want to find its z-score. So z equals 112 minus 100 over our standard deviation of 15. And we're going to have 0.8. So that tells me that 112 is 0.8 standard deviations above the mean. So we can now use our table to find out the percent of values that fall below that. So if we were looking at it before, we'd have our curve with 100 with 112 above it. So this is our normal distribution, and we find the area underneath for below, but we've now converted it to a standard normal, where our mean is 0, and we're doing 0.8 standard deviations above the mean, and now we want to find the area underneath that curve. So we go to our table, and we look for 0.80, and it's going to be 0.7881, which is 78.81%. So 78.81% of our data falls below 112. So each month, an American household generates an average of 28 pounds of newspaper for garbage or recycling. Assume the standard deviation is 2 pounds. Assume the variable is normally distributed. If a household is selected at random, find the percent that generate first between 27 and 31 pounds per month, and then more than 30.2 pounds per month. The important information here is that we're going to assume it's normally distributed. If it wasn't, we wouldn't be able to use our z-scores. So the first thing we have to do, we're going to have to find two z-scores. So we want to be between 27 and 31 pounds. So our first z-score is going to be 27 minus the mean, 28, over our standard deviation of 2, which is negative 0.5. Then our second standard deviation is 31 minus 28 over 2, which is 1.5. So if I create my normal distribution curve based off my data, so my mean of 28, and then we're going 1.5 standard deviations above that, so 1.5 times 2, which is going to give us all the way up to 31, and then we're going half a standard deviation below, which is going to give us 27. So what I need to do is find the area below each of these, and then that will give me the area in the middle. So using our table, we go to 1.5 to get the percent of values fall below that, and we get 0.9332. And then we're going to find negative 0.5, and we're going to find the percent that fall below that, which is 0.3085. And then to do between, we subtract. So 0.9332 minus 0.3085. We're going to get 0.6247, which is 62.47%. In B, we want to find the percent that generate more than 30.2 pounds. So we need to find its z-score. So 30.2 minus 28 all over 2. Which is going to give us 1.1. So if we're looking at our curve, we have our mean of 28 and then 30.2. Now we want the area above. Okay? But in order to find the area above, we first have to find the percent that fall below. So we go to 1.1 in our table, and we get 0.8643 falls below 1.1. So to find the amount above, we do 1 minus 0.8643. And we get 0.1357. So 13.57% of households generate more than 30.2 pounds of newspaper for garbage per month. So next, AAA reports that the average time it takes to respond to an emergency call is 25 minutes, with a standard deviation of 4.5 minutes. If 80 calls are randomly selected, approximately how many will be responded to in less than 15 minutes? So we need to find our z-score. So we have our normal distribution with our mean 25. We want to know the percent that will be responded to in less than 15 minutes. So we want to find the area underneath 15. So first we're going to find our z-score. So z equals 15 minus 25 over our standard deviation of 4.5. So 15 minus 25 divided by 4.5. And we're going to get a z-score of negative 2.22 repeating. Now when you have more than 2 decimal places, we always use just the first 2 and making sure that we are rounding our second decimal place. So we go to negative 2.22 in our table, and we have 0.0132. But this is the percent of calls that are answered in less than 15 minutes. And what we're trying to find is how many calls out of 80 will be responded to in less than 15 minutes. So we take our number of calls, we take our percentage, 0.0132, and we multiply it by the number of calls. And we're going to get approximately 1.06 calls are responded to in less than 15 minutes. Now there is a way to calculate z-score using your calculator. So like, what if the z-score we're given doesn't fall in our table? And so if we want to use our calculator, we want to use the button normal CDF, and then we put our lower bound, our upper bound, and then we put the mean and standard deviation. Okay? And I'll show you in class where you can find this function in your calculator, so you can use that if you're not comfortable with using the z-score table. So now we're going to go the other way. So what we're going to do now is, given a z-score and a mean and standard deviation, we're going to work backwards to find our values. So we know that in order to qualify for police academy, candidates must score in the top 10% on a general abilities test. and it has a mean of 200 with a standard deviation of 20. We want to find the lowest possible score to qualify. So if we're looking at our curve, so we have our mean of 200, and we need some value x to be in the top 10%. So if we're in the top 10%, it means we're looking for the z-score that gives us 90% of our values below that. So we need to look for the z-score that gives us 0.9000, the closest thing to it, which is going to be 1.28. So remember, our z-score formula is x minus the mean over the standard deviation. So 1.28 equals, now we don't know the value because that's what we're trying to solve for, minus our mean of 200 over our standard deviation of 20. So we're going to solve for x. Multiply both sides by 20. We're going to get 25.6 equals x minus 200. Add 200, and you have to get a 225.6. That's the minimum score in order to be in the top 10%. For a medical study, a researcher wishes to select people in the middle 60% of the population based on blood pressure. If the mean systolic blood pressure is 120 and the standard deviation is 8, find the upper and lower readings that would qualify people to participate in the study. So for our curve, we have our mean of 120, and we're going to have two x values because we need to figure out the range. In the middle is going to represent the middle 60% of the population. So that means in our population, so we have 40% left to distribute evenly, which means 20% is going to fall above and 20% is going to fall below. So we need to find the two z-scores that give us that. So our first z-score is going to represent the 20% that fall below. Okay. So we look for the z-score that's closest to 0.2000, which is negative 0.84. And then we need to look for our second z-score. So if 20% is above, our second z-score is going to represent the 80% that fall below. So I'm looking for my z-score that's closest to 0.8000, which is positive 0.84. And that's how it typically works with middles. So if I'm looking for the middle 60% and I'm evenly distributed above and below, my two z-scores should be the same, just one of them is negative and one of them is positive. So I'm going to use these two z-scores to solve for my two different x values. So I'm going to use negative 0.84 to solve for my lower bound. So x minus 120 over 8. Multiply both sides by 8. And we're going to get negative 6.72 equals x minus 120. We're going to add 120 to both sides. And we're going to get our lower value is 113.28. So now we need to do the same thing for our positive 0.84 z-score. So 0.84 equals x minus 120 over 8. So we're going to multiply both sides by 8, and we're going to get positive 6.72 equals x minus 120. We're going to add 120 to both sides, and we get that our second x value is 126.72. So if we're relating this back to our problem, we have that the middle 60% of blood pressures are between 113.28 and 126.72. This is also something we can do using our calculator. So if we want to use our calculator, which again I will show you in class, we're going to use something called INV norm. Okay, and then we put the area to the left, the mean, and the standard deviation. Now this will only give us the lower value, which we would then have to repeat it to give us our upper value as well. But again, I'll show you how to find this function on your calculator when I see you in class. Okay. So please let me know if you have any questions over normal distributions when I see you in class.